Let us begin in the simplest possible way, because the simplest questions are often the most dangerous. You woke up today. You remember yesterday. You do not remember tomorrow. Milk spills, but never jumps back into the glass. Notes can be written, but unwritten notes do not leap back into your pencil. You grow older, not younger. Every experience you have ever had agrees on one thing. Time goes one way. This feels so obvious that questioning it almost seems foolish. And yet, when we open the book of physics and read the rules carefully, we encounter something deeply unsettling. Almost none of the fundamental laws of nature say that time must move forward. They work just as well backward. This is not philosophy. It is not poetry. It is mathematics. Take Newton's laws of motion. Reverse time in the equations, and they still work perfectly. Do the same with the equations of electromagnetism. Still valid. Even quantum mechanics, strange as it is, shows almost no preference for a direction of time. The equations are polite. They do not complain. They run forward or backward with equal ease. Now we have a puzzle. Our lives scream that time moves forward. The laws of nature merely whisper that they do not care. Somewhere between that scream and that whisper, something important happens. Before solving the puzzle, we must be careful about what we mean by time. In everyday language, time feels like a river. It flows. It carries us along. We speak of the past behind us and the future ahead. But physics is not interested in feelings. Physics is interested in measurements. A clock does not measure time itself. It measures motion. A pendulum swings. A crystal vibrates. An atom flips between states. We count these changes and agree to call the count time. In physics, time is not a flowing substance. It is a way of keeping track of change. Already, something uncomfortable is becoming clear. The sense that time flows may not come from the laws of physics at all. It may come from. In physics, time is treated much like space. You can say where something is, and you can say when something happens. Together, these define an event. But there is no symbol in the equations for now. There is no moving spotlight sweeping across reality. The equations describe relationships between events, not a privileged present moment. This is not a minor detail. It strikes at the heart of how we experience existence. To see how deep the problem goes, imagine filming a simple physical process. Two billiard balls roll across a table, collide, and bounce apart. Now, play the film backward. Unless you are extremely careful, you cannot tell which version is correct. The backward motion obeys the same laws as the forward one. Nothing illegal happens. This is true for an enormous range of microscopic processes. At the level of atoms and forces, nature is remarkably indifferent to the direction of time. And yet, real life never behaves this way. We never see smoke leap back into a cigarette. We never see heat flow from cold coffee into a warmer room. Why does a collision look fine backward, but a shattering glass does not? The answer begins with a word that is famous, misunderstood, and often abused: entropy. Entropy sounds intimidating, but the idea is simple. Entropy measures how many microscopic arrangements correspond to what we see on the large scale. When many arrangements are possible, entropy is high. When few are possible, entropy is low. A neatly ordered deck of cards is very special. There is essentially one arrangement that counts as ordered. A shuffled deck can be arranged in an astronomically large number of ways. Almost every shuffle looks messy, not because mess is mysterious, but because it is common. Replace cards with atoms. An intact glass is a very special arrangement. A shattered glass is not one arrangement, but an enormous number of them. That is why glasses break, but do not reassemble. Not because it is forbidden, but because it is absurdly unlike. This idea is captured in the second law of thermodynamics. It says that in an isolated system, entropy tends to increase. Notice the careful language. It does not say entropy must increase. It says it tends to increase. This is a statement about probability, not destiny. Here is the crucial point. The second law is not like Newton's laws. It is not exact in the same way. It is statistical. It emerges only when we deal with systems containing many particles. When we zoom in far enough, the arrow of time disappears. When we zoom out, it becomes unavoidable. Mathematically, this is subtle. The equations of motion written using calculus are time-symmetric. Derivatives do not care which way time points. But when we describe systems with many degrees of freedom, we also describe how they move through a space of possibilities. In that space, some regions are vastly larger than others. Systems naturally wander into larger regions simply because there is more room. That wandering is what we call entropy increase. Time's arrow is not written into the equations. It is written into the statistics. This explains why everyday processes look irreversible even though the underlying laws are not. Once a system moves into a high-entropy state, returning to a low-entropy state is not impossible, but it is so unlikely that it never happens in practice. The arrow of time is not enforced. It emerges. Now let us connect this to your experience. Why do you remember the past, but not the future? Memory is not magic. Memory is physical. When your brain stores information, physical changes occur. Neurons fire. Chemicals move. Energy is dissipated. Heat is released. Entropy increases. To form a memory, you must leave a record. And leaving a record always increases entropy somewhere. The past is the set of events that have left traces. The future has not left any traces yet. This is why you never remember the future. Not because it is hidden by fate, but because memory itself depends on the same process that gives time its direction. Notice how everything aligns. Broken glasses, aging, memory, and time's arrow are not separate mysteries. They are different faces of the same statistical fact. At this point, some people say, so time is just an illusion. That statement is both right and wrong. The feeling of flow is not in the equations, so in that sense, it is an illusion. But the order of events, the accumulation of records, and irreversibility are real physical processes. An illusion does not mean unreal. A rainbow is an illusion in the sense that you cannot touch it, yet it obeys precise laws. Time is similar. The flow is not fundamental, but it is not arbitrary. Now we face a deeper question. If entropy increases, why was it ever low? The second law explains direction, not origin. When we look at the early universe, we find something astonishing. It was extremely smooth, ordered, and low in entropy. This initial condition is the ultimate source of the arrow of time. If the universe had begun in a messy state, there would be no direction to time as we experience it. No stars, no life, no memory. Why did it begin this way? Physics does not yet know, and it is important to be honest about that. Science advances not by pretending to know everything, but by knowing exactly where ignorance lies. What we can say is this. Given a low-entropy beginning and time-symmetric laws, everything else follows naturally. The arrow of time is not a separate law. It is a consequence. Relativity does not destroy this idea. Different observers may disagree about what is now, but along every observer's path, entropy increases and records accumulate. Quantum mechanics adds complexity, but through decoherence, it again reinforces irreversibility through entropy. The same story appears everywhere. Now we face a deeper question. If entropy increases, why was it ever low? The second law explains direction, not origin. When we look at the early universe, we find something astonishing. It was extremely smooth, ordered, and low in entropy. This initial condition is the ultimate source of the arrow of time. If the universe had begun in a messy state, there would be no direction to time as we experience it. No stars, no life, no memory. Why did it begin this way? Physics does not yet know, and it is important to be honest about that. Science advances not by pretending to know everything, but by knowing exactly where ignorance lies. What we can say is this. Given a low-entropy beginning and time-symmetric laws, everything else follows naturally. The arrow of time is not a separate law. It is a consequence. Relativity does not destroy this idea. Different observers may disagree about what is now, but along every observer's path, entropy increases and records accumulate. Quantum mechanics adds complexity, but through decoherence, it again reinforces irreversibility through entropy. The same story appears everywhere.